world. But we want pi to be equal to p. We want to design the Markov chain so we have the right target distribution. P is called the target distribution. That's the language that they use for all this. So how do we do that? Well, what you end up doing is asking for something way stronger. You ask for the detailed balance equations to hold, which I'll describe right now. You ask for, so pi p equals pi. Remember what that means. It means that the summation over all, say, x prime of pi of x prime px prime to x equals pi of x. If you like, That's what invariance means. It's a left eigenvector equation. The detailed balance is something crazy. It says that you take that thing inside, and you ask that I can write that, and it's exactly the same as if I flip x and x prime. All right. Nope. Throw away the summation. So stare at that for a minute. Somebody tell me why detailed balance implies invariance.
This sums up over x tends to 1 over p of x.
Well, P is a transition matrix. So if I sum the left-hand side with respect to x prime, I'll sum the right-hand side with respect to x prime, and the sum of that is 1 for every x. So this definitely implies this. But the converse, no way. This is insanely strong, all right? And so to see what it means, so suppose xt is stationary, and then if I look at the, and so in particular, so xt is distributed according to pi for all t. For Markov chain, that's the same as stationarity. And so take a look at the probability that xt equals x prime and xt plus 1 equals x. That's how I decided to write this down. That's how I'll write it down. Right. So the probability of being x prime is pi of x prime, and the probability of transitioning from x prime to x is px. That's the right stereo interfaces. Okay, so that's Bayes' rule. If I want the joint distribution of xt and xt plus 1, I look at the probability that I'm at x prime times the probability of being there given that I was there. Okay, that's just, I don't know. It's a definition of conditional probability. The conditional probability is this divided by this, right? And then I have detailed balance. Okay, an extremely strong condition, so that's not always true. But then I can reverse engineer this and just say that obviously that's the probability that x equals x and xt plus 1 equals x prime. So basically I can flip time. If I look at the process reversed in time, it's the same as forward in time.
Is it the same as like Markov chain being reversible?
Reversible. So this is called reversibility. I can reverse time, and and the process is identical. And that's a very, very strong condition. So this is reversible.
We
Yeah.
need detailed
No.
balance for reversibility.
What's that?
We need detailed balance for reversibility.
It's equivalent, actually. So basically, I mean, just take a look. I mean, saying this is equivalent to this is the same as saying this is equivalent to this. And I wouldn't have to say t and t plus 1. It would be for any sequence. The whole process can be, the time can be reversed. Statistics don't change at all. So you can see it's an incredibly strong condition. But why is it nice? Anybody have a formula for pi? I know pi. Pi, I don't know. I like x. I don't like x prime. Pi of x is just that divided by that. And I don't care what x prime is. I'll just call it a number. I basically have that pi is proportional to a ratio. So pi of x is so that you'll see this proportionality constants a lot. I mean, if you fix x prime, you can just write this equation here for other x's, and so basically, if you know the process is reversible, you can compute the invariant measure like that by doing this. Let me give a simple example of this computational trick. So it turns out this MM1Q that I gave you before is reversible, right? So remember what that is. I've got the probability of going from x to x plus 1 equals alpha, and the probability of going from x to x minus 1 equals mu, right? And I put a little plus there because I can't go negative, so yep.
Are we still trying to solve MCMC?
Well, I want you to understand the stationarity first. No, I want us to see this thing. I want you to see it first, and I'll give you an algorithm.
Okay, so this is like
I want you. No. We've got this. I said an ingenious trick. I want this ingenious trick to burn into your brains. All right, and why it's useful.
like the motivation for right now.
Yeah, we're right there. How can we construct a Markov chain? So you can solve a stochastic differential equation, go for it, okay? Or you can try to come up with a Markov chain that satisfies the detailed balance equations. This is too hard, the left eigenvector, nobody's been able to do it. There are conferences right now on how to avoid this strong assumption. Can we somehow construct Markov chains where we get the right target distribution without having to impose reversibility? Nobody's been able to do it. This is reversible in the same sense. Yeah. If I mean, forget it, I won't write it down. Now, I want you to understand this ingenious trick, and then I'll give you an algorithm. All right? So the MM1Q, let's write down this equation. Let's take x prime to just be x plus 1. So what would this say? This would say that all right, so this says that, so the probability of going from So let's see. The probability going from x plus 1 to x, that's the probability going down, that's mu. And the probability of going up is called alpha, right? And we gave that a name. This is saying that probability of x plus 1 equals rho times p of x, where rho is equal to alpha over mu. And the less than 1 is for stability. So that Foster's criterion will hold all of that. And so this is a simple linear equation you can iterate, right? You know, pi of x will be rho times pi of x minus 1 and so forth. You get that this is rho to the x plus 1 times pi of 0. All right? So what I've done is, oh yeah, I should have said this, sorry. If if the detailed balance equation holds, then we get this equation, and then we get this conclusion that the invariant probability mass function is geometric. And then you can do is you can say, then verify it. You know, if I take a geometric distribution, does it satisfy the detailed balance equations? And yes, it does. Okay, so an MM1Q is reversible. Okay, so I'm not going to do that testing, it's just verifying what we learned, you know. So basically, again, under the assumption of reversibility, we get this formula, and we say, well, if it is reversible, it's geometric. And then you go back and you just check to see if the equation holds, you know. And it does. It's a one-liner to check that. I mean, reversing those steps is nothing. All right. Okay. All right, so that's a nice fact, is that if you know the process is reversible, computing the invariant measure is always trivial. This is just one example of that. Yep. Yeah. No, never. In control, never. No, it's just sad. I don't know any examples in control where you have reversibility. It's depressing. And in queuing theory, that's it. You know, there's like a few crazy examples. Something called Jackson networks in this queue, and then that's it. Reversibility is depressingly rare. You know, it gives you all sorts of beautiful structure, but no, I don't know of any control examples. If you don't tell me now, but come up with one for me. I don't know of any. Yeah.
Can you have a system, like a physical system that has this?
No, well, the MM1Q, that's the only example I can give you. Yeah, like for a Gaussian linear system, I think there are conditions on the A matrix. Yeah, there are. So there are Gaussian linear systems that are reversible. They require some special structure, some self-adjointness property on A or something on the model. I think I've seen that. I'm not sure. Yeah. Okay. All right, so now to answer the question in the front row. What's it good for? So here's the Metropolis-Hastings algorithm. So what are you given? So we've got our target distribution P. And again, I'm going to choose it to be a probability mass function for now, just because it's easier to write things down. And then I'll explain the algorithm. Nobody ever looks at discrete spaces in this. I mean, it's really rare. And you've got a Markov transition matrix. Okay, so this plays the role of the Q in importance sampling. Basically, P was what I wanted. I can take a Q and sample from that instead, all right? But this is way more clever. So here's the algorithm. So basically, I want to give you a recursion for generating this Markov chain. So okay, at time t, I have my Markov chain takes a value x, and then I draw a random variable, which I'll call y. Independently of the past. So right away you know that you're going to choose k, so it's easy to draw samples from this distribution. You know, just like in importance sampling. You're going to design this proposal distribution. Well, that's a proposal distribution. All right. Okay. So is the next state could be y? No way. If you just said that's xt plus 1, you would get a Markov chain with transition matrix k, and who knows what you're getting. Right? So what you do is you then come up with an acceptance probability. So you define this function of two variables, and you plug in x and y to get your probability of accepting this proposal. And there it is. Isn't that cute? Can you imagine a simple algorithm? That's it. All right, so you got this? Look, I mean, how many lines of code is this? I mean, you have to have this to be simple, so you can draw the rand command or something, rand m, to draw y. And then you have to be able to plug in the numbers here. So you have to be able to look at this ratio. And then you have a, well, what's the Bernoulli random variable in MATLAB? I don't know. And you basically have to be able to flip a coin with this probability and accept the proposal with probability of a, x, y, and reject it with the remaining probability, so you stay still. All right? And guess what? It does everything. It's irreducible. Well, let's go through and look at this.
Oh, so
Yeah, go on.
K is another kernel matrix.
K is your choosing. So you get to choose anything you want, although clearly there should be some restrictions. You can get in trouble. Like
P.
so a kernel, K being the identity matrix wouldn't work. You just stay still.
Well, yeah, that'd be,
That'd be
if
bad.
you started in that state, you'd always.
Exactly. You'd be stuck forever. So you could ask some questions. So irreducible? Well, you could just impose some conditions on K. Just make K positive everywhere. Then you can get anywhere. All right. And P as well. Because you might as well. I mean, you might as well just take the states for which X is, throw away states for which P of X is 0. Who cares about those? Just toss them. And so, you know, all the algorithms we look at have this property. This is positive everywhere. Aperiodic, we can imagine it's likely, because as long as A is less than 1, sometimes you get stuck. So if so the probability of staying still, if at one point X is positive, it's aperiodic. Just look at the definition. So this is not very important, aperiodicity, but you know, you might like to know it. And so the fact that you sometimes get stuck gives you aperiodicity. And then finally, detailed balance. Of course. That's the beauty of this. It's like it's nothing. I'm not going to do it. It's just annoying. It follows from the representation that yeah. Where is it? Oh, I thought I had it here somewhere. I mean, it follows from, if you can write down the transition matrix. So basically, you can write down the transition matrix. It's just basically A times K plus some remainder times the delta function. You know, I mean, this is discrete time and space. So by direct delta function, I just mean this is 1 if y equals x and 0 elsewise, otherwise. So R of x is the probability of staying still. Right? And how do you find R of x? You just sum both sides. So if you really want a formula for R of x, you sum both sides of this equation, right? And you get this funny dot product here in the middle, which is a function of x, right? And the sum of this over y, well, that's just 1 if x equals y and 0 everywhere else. So the sum of this over y gives you 1, all right? So basically, this is parenthetical, really, but if if you're willing to do the algebra, you multiply pi of x by both sides, p of x on both sides, and you notice there's a p of x here, and things cancel out, and everything, detailed balance holds. I'm not going to derive it. Yep.
This goes back to earlier, but it's still not making sense to me how this works, because to be able to take K, you need to know something about it.
Nothing. Nothing. That's what's so awesome. Nothing. Just take K to be uniform. Well, I'll give you examples. Anything? Do you have another question? Because it'll really help if I give examples. You'll see nothing. It's awesome, you know. Although to make it work well, it could be as bad as importance sampling if you don't, you know, a little bit careful. Yep.
What do we know about like mixing?
I love it. Well, let me say some. So, reversibility. Remember, I was yelling about Jordan, how I hated him, and repeated eigenvalues and all that stuff. Reversible Markov chains don't have those problems. They're diagonalizable. You know, you have repeated eigenvalues possibly, but there's a basis of eigenvectors. So, I mean, what a coincidence. So this morning, a colleague at Illinois sent me a paper on the spectral gap for reversible Markov chains. And so you can actually get bounds on mixing times on the rates of convergence without not nearly as much trouble as in general. So yeah, it would take too much long to get into it, but I can send some notes. But I shouldn't use blue. That's right. Yeah, so there's a big theory on getting bounds on rates of convergence of the process to stationarity under reversibility. Without that, it's a minefield, and it's all because of the intuition about Jordan form. You know, it's really the issue. When the fact it's basically in the finite state space case, it's diagonalizable. That's one thing you get. All right. Okay, so let me give you an example. So
What was meant by mixing times, even if
no, I mean, it's just that I don't want to really get into it, but so I'm just saying rates of convergence. So we know that a finite state space Markov chain is geometrically ergodic. You know, it converges the distribute. So we know that the probability of going in n steps from x to y goes to the steady state at geometric rate. Really the question is what's the rate? And we can get bounds on the rate for reversible Markov chains, and there's a big industry for that. If it's not reversible, you know, put your hands up in the air. There's very little. Yeah. And that's important because we're going to be simulating. So if this takes a long time, you know, then we're sampling from the wrong distribution. You know, if this takes 1 million years to be close to pi, then when we're doing it, the law of large numbers, then it's going to take forever. So we want this to be fast. Yeah. Remember, we're trying to sample from pi, not from p to the n, all right? So we want that to be.
This is what our mix was?
Oh, you know, I'm just saying, this is, so X is a Markov chain, so you got to ask, what is the transition matrix? And I'm claiming it's a scaled version of K plus its remainder times the delta function. It's what you get from this. You either transition according to K or you stay still. So R is the probability of staying still. Yeah. So it's just 1 minus this, yeah. Okay, cool. So the first one's called the independent sampler, and this definitely answers your question. Just don't worry about x, just draw it independently. All right. And then this should be pretty easy. So the probability of accepting, this will just be, you know, P of y, Q of y, right? I mean, x. Check this carefully. So ky to x will be q of x for all y, you know, and kx to y will be q of y. That's what the independent sampler says. I just don't care what the previous state was. And if you look at it carefully, that looks like a likelihood ratio. So the notation that I adopted, this would be the minimum of 1, and I flipped my likelihood ratios today, making it P over Q, so I get the likelihood ratio at y divided by the likelihood ratio at x. Now, all right, and there it is. I'll maybe draw a sketch in a moment, but there it is. So you look at the ratio of likelihood ratios, my previous likelihood ratio and the new likelihood ratio. And so if the new likelihood ratio is very big, then this minimum will be 1, and I'll accept for sure. And if I get a new likelihood ratio is very small, it's unlikely, P over Q is small, then my probability of accepting is small. All right, that's one. So but the Metropolis sampler is a little tweak on this. Instead of, I'm not going to ignore the past anymore. Let me draw it like this. This is the most natural thing to do in the world. Actually, I'm going to make it a little funky just for fun. Oh, yeah. I'm going back and forth now. Remember I said I was going to go back and forth between densities and discrete, density and discrete? It's up to you. You can consider this a density or discrete, it doesn't matter. So I'm drawing this continuous. In my brain, it's a density. If you like, I'm looking at the integers, and I'm just looking at the probability mass function, because it doesn't make any difference. The algorithm is identical, whether it's densities or discrete. So the Metropolis sampler, your kx to y is this. So this, I'm taking a point x, and I'm sketching for you is kx to y as a function of y. X is fixed. So I'll put a knot there just to emphasize I'm fixing a particular x. And what's special about this is that my proposal distribution is centered around the previous state, and you see the symmetry. Okay? Those two things are crucial. Right? And so this is symmetric. You know, I try to make it so if I flipped it on the vertical axis, it'd be true. And by symmetric, I just mean that q of x equals q of minus x. And that's called the Metropolis sampler. That was the first, big algorithm that came about in the 40s, and then Hastings improved it. So this is a Hastings Metropolis algorithm. Basically this general result. The Metropolis sampler is this very special case, right? And And let's take a look at this. So I've got my P of y, and I've got ky to x. Ky to x would be q of x minus y. And I've got kx to y, that's q of y minus x. Right, y'all with me? But then these cancel out by symmetry. So that's why the symmetry is assumed. So two really elegant algorithms, and this is by far the most elegant. I mean, you just look at the ratio of the densities or the probability mass functions, either way, it doesn't matter, and minimize that with 1, that's your acceptance probability. It couldn't be prettier. So that answers your question, right? I mean, plug and play. Just give me any old Q you like and go.
But I mean, so what happens, like, say you think Q is very far off?
All right.
You're always gonna update it.
Okay, I'm going to pay you that $50 afterwards. All right, so before I agree with you and amplify your point, one thing that I want to loudly declare is one of the reasons people are so excited about this algorithm is